Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everybody, I hope you are enjoying the course. So now we are going to speak about one professional element, which is timers. We already spoke about them previously when we spoke about the interrupt, but today we will go through more details about the timers. So this is module 10. By the end of this module, we are going to understand the different timer modes and the timer frequency. We will speak about Prescalar, so we'll understand Prescalar better, and we will speak about the registers. Of course, as any device inside the microcontroller, to control this device you need to change the bits in some registers. The timer itself is a register, but the value of these registers increase or decrease automatically. So the 8-bit timer is capable to count up to 2 power 8 to 5, 6 steps, which is from 0 to 255. So if we go to the calculator, as you can see, if we have 8 bits, so 8 bits in decimal is 255. So the counter can count from 0 up to 8 ones, 1 1 1 1 1 1 1 1, which is equal in decimal in 255. Now if we have 16-bit, so this is equal to 65535. So the timers of the microcontroller, we have even 8-bit or 16-bit or sometimes more. The 8-bit will count between 0 to 255, and the 16-bit is able to count between 0 and 65535. So once the register of the timer reach its maximum, the max, it will return back to the initial value, which is 0, and the timer counter will give an overflow flag. In Atmega 32 and also in Atmega 32.8 actually, we have 3 different kinds of timers. Timer 0, it's 8-bit timer. Timer 1, 16-bit timer, and timer 2 is 8-bit timer again. So these 3 timers can be either work in 3 modes: normal mode, CTC mode, or BWM mode. So we have the normal mode, which is counting from 0 to max. CTC mode, which stands for clear timer on compare, so it will count up to a specific value defined by the user. And there's what's called the BWM mode. We'll speak about it later. Speaking about timers, we need to speak about the timer frequency. So if we have a frequency of the CPU of the microcontroller, so the clock, the internal clock or the external clock, if it's 4 megahertz, that means the period is the inverse of the frequency of the clock, which is 1 divided by 4 mega, it's 0.00025 milliseconds. So for every transition, that means from 0 to 1, from 1 to 2, of course it will be in digital, so from 0 to 1, from 1 to 10, and so on, each step will take 0.00025 milliseconds. Now if you want to make a delay using the timer, you need to count how many steps you need to wait until you finish your delay. Okay, so one step is not 1 second, one step is this amount in milliseconds, so it's dependent on the frequency of the microcontroller. So to calculate the timer count that is needed for a special delay, we divide the required delay in milliseconds or in seconds divided by the clock time period, which is this one, the period. Okay, then minus 1. For example, let's say we want to make a delay of 8 milliseconds using a microcontroller with frequency of the CPU 4 megahertz. So we calculate the period, we already calculated before, so it's 0.00025 milliseconds. So the timer count should be 8 milliseconds divided by this value minus 1. The result will be 31,999. So the clock should take 1,999 times to make a delay of 8 milliseconds. Okay, of course this number cannot be applied in 8-bit timer. We need at least 16-bit timer, because the 8-bit timer, the maximum is 255. After that it will overflow. Of course there are some techniques we can still use the 8-bit timer even by Prescalar or by other techniques. But if we want to use it in the normal way without any modification, we need to use the 16-bit timer because it's capable to count from 0 up to 65535. So this number will be in the range. Prescalar, what do we mean by prescalar? Prescalar, actually, as we said before when we spoke about the AGC and the interrupt, it's a division factor. So the division factor will divide actually the frequency. So let's take this example. If we have a 4 MHz CPU, a 16-bit timer with the maximum of 65,535, we can get maximum delay of 16.384 milliseconds. How we calculate this? Just multiply this by the t, okay, by 0.00025. Now, is 16 milliseconds is sufficient delay? No, of course. Sometimes we need to make a delay for 1 second, 2 seconds, and more. Let's say, for example, just we want to make 25 milliseconds. What should we do? So the solution that the microcontroller manufacturer provide is the technique which is frequency division, which is pre-scaling. So actually we don't reduce the actual frequency, but we derive frequency from it to run the timer. So instead of making a transaction every 1 clock, so it will be waiting some clocks and then make the transaction. So this will make the time longer. The AVR offers many dividing factors or prescalars. We can choose for timer 1, 8, 64, 256 and 1024. So a prescalar of 8, that means we divide the frequency by 8. So the effective clock frequency will be the nominal frequency, this one, divided by 8. And if we change the prescalar, we'll change the division factor. Timer registers. Always I put this image to make you understand how to control using the registers. So each timer has 2 specific registers, and there are other registers which is shared between the timers. So we have 3 timers in the Atmega 32. So the value of the timer 0 is stored inside TCNT0, timer counter register. Okay, so in this register the value of the timer is stored. So the value of the counter is stored here and decreases automatically by the clock pulses. Data can be both read and written from this register. So you can put a value and then run the timer to increase step by step, 1 by 1. The other register for timer 0 is TCCR0, timer counter control register. So the first 3 bits in this register are for the prescaling. So if we put 000, that means no clock source, that means the counter is stopped. If we put 001, it's no prescaling, and then 0108, 011, 64, and so on. They are 110 for external clock on falling edge and on rising edge. So this timer can accept external clock, and also it provides the prescaling using these 3 bits, CS00, CS01, and CS02. The other bits are actually used to decide the mode that the timer is working on. So we have WGM01 and WGM00 are for waveform generation. So according to this value, the timer can be worked in normal, BWM, phase correct, CTC, and fast BWM. For the COM01 and COM00, they are compare match output mode. So you can choose the normal board operation and clear OC0 on compare match, set OC0 at top, and set OC0 on compare match, clear OC0 at top. So these are for the CTC mode, and also for the BWM. We will speak about this later when we explain more about the BWM. Timer 1 similarly has 2 registers also. The counter value, which is stored in TCNT1. So as you see, it's 16 bits. So actually we have TCNT1H and TCNT1L. Also it have the TCCR1. It has A and B. So for example, we will make B because B has the prescaling definition. So it's very similar to timer 0. and these are used to define the mode of the timer. We have TCCR1A and TCCR1B. Okay, so in TCCR1B we define the prescaling, and the other bits also are used for waveform generation and compare match mode, which are related to PWM and CTC. Timer 2 also very similar to timer 0. The difference is the division factor of the prescaling. Also it has TCNT2, which have the value of the counter, and the prescaling, the difference is here actually, it has more modes. So we have A, 32, 64, 128, 256 and 1024, and it's not supporting external clock. If we go back to timer 0, as you see, the numbers are as you see that we have only 8, 64, 256, 24 and 24 external clocks. Here we have extra 2 division factor, which are 32 and 128. Again, WGM and COM are for waveform generation mode and compare match output modes. Now the common register. So as we said, each timer has 2 registers, and there are other registers which is shared between the 3 timers. The first one is called TIMSK register, interrupt mask. So as you see, we already discussed, we have TOI E0. This is for enable the interrupt for timer 0, enable the interrupt for timer 1, and enable the interrupt for timer 2. So it is overflow interrupt. Okay, we have the OCIE, which is to enable the compare interrupt. So OCIX, timer counter X stands for 0 or 1 or 2. It's the output compare match interrupt enable. Enabling it ensures that the interrupt fire whenever match-well occurs. We will see more in the tutorial or the examples in this module. Second common register is the TIFR registers, the interrupt flag register. So this is giving the information that the interrupt occurs. So when the overflow happens, in timer 0, TOV0 will change to 1. Okay, this bit is set to 1 whenever timer overflows. The bit is reset to 0 after calling the ISR, the interrupt service routine. So when the interrupt service routine is executed, finished, it will go back to 0, waiting for another interrupt to happen. OCFX is output compare AB match flag bit. This bit is set 1 by the AVR whenever match is occurs. That means if TCNT equal to a variable OCR, as we will see in the example, it will be set to 1, and when the ISR is executed, it will be returned to 0. Now remember that AVR provides us with 2 options of counters or timers. We have 8-bit and 16-bit. 8-bit for timer 0 and 2, and 16-bit for timer 1. 8-bit will count only up to 255, and 16-bit can count up to 65535. In other words, an 8-bit timer, its maximum is 255, and the 16-bit timer, the maximum is 65535. As we said, timers also have 3 modes. The normal mode, which we are discussing in this module. The CTC mode also, I will give example about it in this module. And finally the PWM, which is related more to controlling motors or other things. I will speak it in next module. So let's understand how the difference between normal mode and CTC mode. So in the normal mode, the counter signal will be like this. So the value of the counter, which is stored in TCNT 0, for example for timer 0, so the value will start from 0, it will increase up to 255 for timer 0 and to 65535 in timer 1. So this is the max, so it will increase until it reaches the max, then it will overflow and go back to 0, and increase again, reach the max and go back to 0. So it overflows back to 0. This is the normal mode. For the CTC mode, we have a compare value which is less than the maximum. So the top never exceed max. Of course, the top, that means the value that the compare is reached is less always than the max. So the timer will increase until it reaches the top and go back to 0 before it reaches the max. So it will reach the top, go back to 0, again increase until the top and go back to 0. So we need to define between max, which is the maximum value that the counter can run to, which is 255 in 8-bit and 65535 in 16-bit. The top is a value that defined by the user, which is always less than the max. So that's all the theoretical part about timers. We'll see examples in the videos. Thank you for listening, and I hope you are enjoying this course.